Hello and welcome to the Friday afternoon projects. This time, in part 3, we'll be trying to take our little toy language and finally get to the point where we're actually using LLVM to evaluate something. So by the end of this part, hopefully we should have implemented something which is essentially a JIT-ed calculator. It will take an arithmetic expression in, work out the answer, and print out the result. But it will have done this via LLVM, and in principle it will have JIT-ed it into machine code. Right, we've logged back into our development machine, just as we've done before. So let's re-enable tmux and change to the appropriate directory. And here is where we were before. So let's activate the virtual env and let us start IPython. So we're back here at the notebook, and this is where we left off last time. We're going to be using LLVM, and so I want to have a quick play with LLVM and see if I can actually work out how I'm going to evaluate an expression with it. So I know that there are LLVM bindings to Python called LLVM Pi, so let's make sure we've got the virtual env activated, hard thing to say, and install LLVM Pi. LLVM Pi install. Can't spell today. There we are. And LLVM Pi is successfully installed. So let's see if it actually works. So we'll create a new notebook and we'll call this LLVM Playground, because this is where I want to sort of learn how to use it. And let's also have a quick look at the LLVM Pi webpage. So let's have a look at the documentation. This is the version we just installed. There's a user guide and an introduction. So what I'll do is I'll have a quick read through of this and come back when I have done so and hopefully know what I'm doing. Right, okay, I'm back. Had a read of it. I cut that out, obviously, because it's not very interesting to see me scroll through a web page. But here's what I think. So first of all, the module is called LLVM, which is very easy. And LLVM has this concept of modules, and modules is what would be an object file, I suppose, in traditional notation or traditional phraseology. So let's create a new one. And in fact, actually, we need to import LLVM core, and I'll call that LC. It turns out that LLVM's Python bindings have this sort of rather unique way of creating things, that you have to use this new class method. Don't quite know why. But you can see here that IPython has handily popped up the documentation for it. And I'm just going to call this module test. So I can actually print that out, and you see that you get the LLVM source code for an empty module. So it's just got its module ID. Not as exciting as it could be. So let's add a function, and our evaluation function is going to be a function that takes nothing and returns a floating point value. So let us do that now. In fact, actually, let's try creating a function that takes a value and adds 3 to it. I think that's probably going to be more interesting. So we need to create a function, and LLVM has base types which sort of mirror the host types, but it also has, interestingly, function types. So we're going to be passing floats around, so let's just create a float 32 type, which is done like this, I think. So there's a built-in type in LLVM called float, and my eval function is going to have a type of a function. And what does this take? It takes a return type and parameters types. So it's going to return a float. That's going to take in a single float like this. And now I actually want to create that function. So do I do add function here? What does that take? Adds a function with a given type with a given name. That's right. So I want to create my new function. It's going to take, let's call this of type eval func, and I'm going to call it test1. So now what happens if I print my module? There we are. I've declared a function inside this module which takes a float and returns a float. So I need to give this a body now. So I think the way one does this is something like, is it pen basic block? Yes, that's right. So we can get a block, and we'll call this entry, or we'll call it BB I'll give it the type of entry. So this will be the actual function body, and it's called a basic block in LLVM terms. Essentially, it's a group of statements that either ends in a return value or ends in a branch, which are called terminals, apparently, in LLVM speak. So if we print the module out, there we go, we can see we've got actually now an empty function, which does nothing. So we could just add a return value to that, and to say return 7. But let's actually try to be sensible about this. So I think the interface you do this is by something called an instruction builder, which do you get from the basic block? Or do you? No, that's right. So the instruction builder is done something like this. Is it new? There's some of the basic block. So this will give me a class which lets me add functions to that basic block. So the first thing to do is going to be add things together. So I want the add2 to be what do I have? Gosh, all of these things here. Is there a floating point add, or is it just normal add? Let's see, let's try fadd. There is an fadd, right. What's that take? That takes a left-hand side and a right-hand side. Well, the left-hand side is going to be the first argument of the function. So let's see, f.args, maybe, yep. And then presumably 0 is the first argument. And then I want to add 2, which means it needs to be a constant value. And I think that's something called constant, and then float, or real, there we go, real. A real of type 32, and with a value of 2.0. Not a string value of 2.0, obviously. And that should have hopefully added it to the builder. So if we print the module at the moment, yes, you can see here we've added a function which adds so %0 is obviously the first argument of the function, adds 2 to it, and then it's given the value of %1. And we just want to return that, so that's not too hard. So let's add a return value. Return, and then this just takes a value, doesn't it? Yes, and that's obviously just our add2 value from above. So print that. There we go. We've got it brilliantly. So that's the function defined, but how do we actually run this? And that's the thing. Well, this is where we need something called the execution engine. I think it's called, is it LLVM.engine.ee? There we go. And we'll call that LEE to make it easy. So I think we need to create a new, is it engine builder? There we go. So we create that with the module. So our engine builder is this, and an execution engine is something like either it will interpret it, or it could compile it, or it will JIT it. We actually want to JIT it, and the engine builder will choose the right thing based on the machine we're actually on. So it should hopefully create a JIT-ed one from this simple one here. So let's actually create the execution engine. I think you do that by just create, I think. You'll notice here that you have various things like force interpreter, forcing JIT, things like this, to be able to select the target. Let's just let it choose its own thing, because we assume that it knows probably better than we do at this stage what to do. And so that's the execution engine going, and I think we can just run it. I think we just have to do run function. The actual function, which we know is called f. In fact, let's try to be really good about this. Let's say, do we get the module out of this? Well, we know it's in the module M. We shouldn't even get the function named, and we know it's called test1. So we run that, and then what does this take? It takes the arguments, which presumably must be an iterable like this. So we need to put the first argument in here. Now, I don't think you can just do something like this. Yeah, because it says argument is not an instance of core generic value. So I think it is something like, is there a generic value? There we go. Generic value. Is there a constructor? Oh, there we go. So that's construct. So let's create something of 32, and we'll create it with a value 43. So this should give us a return value, but of course we don't know what that return value is because we haven't printed it. So RV equals this. Can we print RV? Can. And we want it as a real. We tell it what type it is. It's that. 45, and that's correct. So let's just combine these two cells together. Merge cell below. There we go. So we should be able to put 15 there. And there we go. Our add to function is working. Good. So we just need to generalize this process for our existing compiler. So I think the easiest way to do that is, first of all, in our AST nodes, let's add some way in which these can actually start returning an LLVM value. So here we have 2 dict, and I think all we need to do is just add 2 LLVM value. For the moment, I'm going to assume that all of these things have value type of float. So let's import LC, and let's create a float32 type, which is, as we saw before, lc.type.float. Good. Now the integer literal class takes an integer, but we're going to convert that to a floating point. So in fact, actually, a 2-value function, which is going to return the LLVM value of this node, is actually going to be really simple. We've already done this in the playground. We found out that we had to use the LC constant real. So let's in fact just copy that into there, and instead of 2.0, we're going to be self.value. And magically, Python should convert between the integer to the floating point for us. So we've done a lot of work already. In collection, oh no, of course not. I've not imported from all the way. There we go. So that should give 2 dict, and then let's just also check up here. We can do 2-value. And we get something. Oh, we haven't actually returned it. Oops. And we get that, which is good. And then presumably we can do as real. Constant FP hasn't. What has it got? F dot. Did I just do that? No. Oh, I wonder if we... Oh, no, of course, we'll just need to put it directly into a generic value. Yeah. Okay, well, I'm fairly sure that's going to work. Well, no, we should probably just check. So can we do that? Does that work? Is there a real floating point? No, that doesn't work. Perhaps we can do that. Oh, okay. Is that a class function? Oh yes, I see. That just takes right like this. A float is required. Oh dear. Perhaps we're just going to have to assert this is going to be correct. It does say it's a constant floating point value. So can we actually? Well, I think we'll just have to hope it's correct for the moment. So the unary operator, 2-value, it's going to look something like this. So if self op is plus, we don't actually need to do anything. So right hand side equals self right hand side dot 2-value. So we just need to return the right hand side. If it's minus, we just want to return. So in actual fact, this is where we need to insert an instruction, but we've got no instruction builder. So I'm going to say that this takes a context, and the context will have an IB attribute, which will be our instruction builder. Yeah. So return context dot IB. So let's just kind of hope this works actually. Now what was it? It was fadd, so I'm going to guess it's fmul. And we want to multiply the right-hand side by -1, don't we? lc.constant dot real type float 32 and value of -1.0. Okay. Actually, now this 2 value won't work. So let's just delete this. So that will do. Oh, we should probably put else raise value error. In fact, let's just assert. No, let's raise and not implement it. Error. Right, binary operator expression is going to be very similar to the unary operator expression. Except for here we need to get the right hand side and the left hand side. Like this. So now if the operator is plus, in fact I basically want to do something like this. So plus it's fadd the left hand side to the right hand side. If it's minus, it's f sub, presumably. And then the same for multiplication and division. So it's going to be fmul and fdiv, presumably. Mul and div. There we go. So that should be the binary operator expression working. Okay, so let's save that and see if it's actually going to work. So let's create a new notebook called compiler. So let's remind ourselves how parsing works. So binary operator, always expression. Okay. So we need to import expression from parsing. In fact, let's just import parsing, it's lexing, isn't it? Lexing. And we should probably directly import the AST nodes. So let's just check that we can do the parsing. So there we go. In fact, someone pointed out to me that this parser is stupidly complicated, because what we've actually done here in parser base is defined a class that kind of is called with parse and then sets a single argument. So this is kind of almost exactly equivalent to just a function call, but there's a slight wrinkle that we've folded this pop expecting in. So actually this is not possibly the best way I could have implemented all this parser thing, because you notice here that essentially all of these parsers are just rather sort of complicated wrappers around a single function. But I think I'll leave it as it is, because I don't really want to do any large-scale refactoring at this point, but that was a bit of a sort of design error, I suppose. The practical upshot is that basically I just have all these dot nodes knocking around, which is always quite annoying. But there we go. Anyway, where are we? Parsing compiler. So, in fact, actually, let's from parsing import expression, and from lexing import lex. So I should be able to do that. We don't have a token stack, because that should be like this. Okay, good. So let's create a function called parse expression, which takes in some text and just returns this. So we should do 5 times 7 plus 1. Woohoo! So in principle, if we can just call to value on there. Oh, we need to create. So let's create a function called add expression function which takes in some text. So first of all, we'll parse the expression, and this is going to return a function. It's going to add a function to a particular module, which will parse that which will evaluate that expression. So we want to first of all parse the expression. Then we want to create a module which will evaluate the expression. So in fact, actually, because we need to create, well, no, we know that the function for the moment is going to return we know that the function is going to return a floating point value. And so we can just hard code for the moment that the return type is going to be a float. So the function type is LC type dot function rep type, and it actually doesn't take any arguments. So f equals module add function. We should probably give this a name. So add a function called name, and then we just do what we did in our LLVM playground. So we create a basic block, a builder, and that can be part of our context. So in fact we should probably give the context, yeah, let's just initialize it with an instruction builder for the moment, like this. So the basic block is lc.basic, it's f.append basic block, isn't it? f.append basic block, and let's call it entry. The instruction builder is builder.new, and then you get past that the basic block, which is like this. And then we want to get the actual value of the expression. So RV is the return value is the expression to a value, passing it this context object that we expect. The reason that I've wrapped this IB in a context object is because probably later on this will have things like symbol tables and what have you in, things like that. So I'm trying to sort of future-proof the design so I don't have to change too much of the interface. That's a bit invalid syntax, that's right, because I actually don't, so that's what I meant. So that should have appended all the instructions to that basic block, which means we now just need to add a return value. So it's ret, isn't it? tabu.ret, the return value, and then we need to return the function. So let's see if that works. If it does, it's amazing. We've essentially got a parser working. So let's create a module. LLVM.module, lcore.module, new test, f equals add expression function, which will be 6 times 7 plus 3. To that module, we'll let it have the default name. So it's an add function requires this module add function. Oh, of course, we need the type, don't we? So actually, that's right. This t-value with context. That's true. It is. Where are we? There, we need to pass the context in, don't we? That's the whole point of having the context. There, and we need it for the uniopera as well, don't we? There we are. So save, let's restart all this. And run all. Okay, that's worked. Jolly good. And that should be all we need to do. So let's then create an engine builder. Have we imported? We have. Module, execution engine equals engine builder create, RV equals run function, f. I think run function just takes the function, doesn't it? Run function just f, and then we need to pass in that. We don't actually need to pass in any input values because it doesn't take any. And then what happens if we have rv dot, is it as real? Where are we? As real, and then the type, which we need to import from AST nodes. From AST nodes import code. There we go. Run a function missing one position. Oh right, okay. Need to give it. In fact, it's got no arguments. There we go. Have the answer. Is that right? What is 6 times 7? Well, luckily, actually, of course, we have a parser built into Python which tells the answer. Yes, indeed it is. Good. So let's roll this up inside a function called eval expression. Oops. Do that. Put in text here. So let's try some hard things. First of all, numbers. Yep, that works. 2 plus 5, that is what we want. 2 times 5 times 2 should give us 5 times 2 is 10, plus 2 is 12, that's right. But if we do brackets here, we get what we expect, 7 times 2, and then add 9. Yes, that does the right thing. He said just doing it in his head. And let's take the whole thing and divide that by 2. There we go. So, very simple. We've written a function which will evaluate an arithmetic expression, but we've got most of the plumbing required to actually get our LLVM based compiler up and going. We've worked out how to create modules, we've worked out how to compile them. So this, of course, has been JIT-ed to actually generate this value. And next time we'll see if we can't start doing things like adding some some variables in, so we can do some interesting things. But for the moment, we need to save this. Close that. We need to save this. I need to save this. Standard page, because I'm going to save that because that's quite useful. I need to go back to here, see where we are. Right, we need to compiler and that. So git commit -a. And now we can parse and evaluate expressions via LLVM. How exciting. Okay, so that's it for this episode. Quite a short one, but we have got a lot of, we've sort of joined the loop, as it were. We've now got all of the base we need in order to be able to start doing some more interesting stuff with the language. So as I said, see me next time when I'll start to add something like variables.